بسم الله الرحمن الرحيم. So lecture 9. February 9th, sorry, 2022. And today we talk about quantization. Inshallah, today and the recorded lecture, tomorrow hopefully I will record it. We'll finish this, what we want to cover from this chapter. So today, the whole lecture will be talking about quantization error and how to characterize it and how to calculate the signal to noise ratio based on your quantizer quality in terms of how many levels we will be using. Okay. So from last lecture, we are in the under the general theme of analog to digital conversion. And if you recall, we said we have 3 boxes. This is in case we don't want to send our signal directly. We want to digitize it and then use digital modulation. We don't want to use AM or FM directly. We want to convert the signal to ones and zeros and then we modulate it. Why is that? So there are many advantages for you can process it, you can encrypt it, you can do a lot of things using just a pure processor if you convert your signal to ones and zeros before you transmit it. So the original signal, this is M of t. We said this is continuous in time and amplitude, and the first block is we sample it. So we end up with discrete in time, but continuous still in amplitude. And then you get into the quantizer that we will be talking about today, so that you end up with discrete in time and amplitude. And the last step, which is usually combined with the quantization, which is encoding. And here your signal will be transformed into series of ones and zeros. The book has like 2 or 3 sections on sampling. I will not spend time on sampling. I will just mention 2 things. So in sampling, very quickly, given M of t has maximum frequency of B, then according to Nyquist, then we should use a sampling frequency of at least 2B, right? For us to be able to reconstruct the signal, for us to be able to reconstruct the signal. So if this is my original signal M of F, this is F, this is M of F, this is B, this is minus P. So if we sample the signal, how does sampling translates in frequency domain? In time domain, it's just multiplication with a series of delta function, delta train or impulse train. In frequency domain, we are repeating the spectrum. Of course, there are some scaling at multiples of the sampling frequency. So if fs is greater than 2b, this is what you will get. So this is b, this is minus b, this is fs, this is 2fs, and so on. So you have infinite number of replicas for the signal. However, if fs is less than 2b, what happens? What do we call this phenomena? Aliasing. Why we call it aliasing? What's an alias? Smoothing? So you have an email alias. What does an email alias mean? If you have, like, if one of you is IEEE member, they give you an email alias. What does it mean? It's more or less like a fake email, right? You see whatever, Muhammad@IEEE.org, but basically there is no email server that you can go and log in and check your email. It's just being forwarded to another email that you identify. So this is an alias you put, and then it's very famous that if you work for any place and then you want to leave them, they will tell you will keep your email, but we'll forward your email to another account. So you'll not be able to log into our system and check your email. So your email becomes just an alias, so a fake email. And that's what happens here in this region, aliasing. What you will see at the edges, there will be an overlap. What you will see is not the real signal that is originally there in the baseband, but it's a fake signal because of this overlap. You see the overall, right? You will not see the original signal. What you will see is not the real signal. It's a fake signal. It's an alias signal. And that's why it's always the case before sampling, we use an anti-aliasing filter with a width of 2b. So you try to cut the signal with a width of let's say it's fs. Yes, you want to cut the signal so that it does not overlap. In this case, if you are using fs, so your signal, if you're you want to make sure that fs is greater than 2b, right? So you want to chop the signal at what? You want to make sure that fs is greater than 2b, right? So your original signal, you should use what type of low pass filter if we're talking about baseband signal? So you cut at b. If you're using frequency fs 2b, you have to cut the signal at b. That's why we cut the speech signal, for example. We said, I think next time or today, I'm not sure if we reach that point. If original phone signal, they use a sampling frequency of 8 kilohertz. You sample the voice signal at 8 kilohertz. So we cut the signal at 4 kilohertz. Okay, so that we do not, because there are weak components greater than, we know the voice signal can extend, or any audio signal can extend all the way to 20 kilohertz. But we want to cut it so that when we sample, we don't, the replicas of the signal do not overlap. Okay, and yeah, I will not talk again, as I said, about reconstruction of the signal. We did this in signal and system. So sampling is important, but we covered this before. So let's focus on quantization. which is the next box. And again, quantization, as we mentioned last time, is just like rounding, right? So converting the signal that is continuous in amplitude into a discrete amplitude signal through rounding. And we mentioned last time the famous example of clothes. When you want to buy shoes or a pant or a shirt, there are specific sizes that you round your body to, and then you buy what is more comfortable to you. Quantization, there are many ways that we can quantize the signal. We can divide quantization into scalar quantization or vector quantization. So I can quantize each sample at a time, or I can take two samples in 2 dimensions and I create regions, and then I sample 2 samples at a time, which usually produces less error. We'll cover only scalar quantization. Also, quantization can be uniform or non-uniform. Uniform means your levels of quantization are the same, of equal distances, equal widths, all the levels that you use in quantization. However, non-uniform, we'll see that it's better to use more levels when you have more signal or more probability of having the signal in a certain region. You use more levels. Like, for example, not sure about the shoe sizes. And for men, probably the most probable shoe size is 42, 43, 44, 45. So if I have a shoe company, I can have more levels. Like I will have 42 and a half, 43, 43 and a half, 44. I will have more levels so that most of the people are in that range. But it's very rare to have a guy with like 36 shoes. There are, but I will have 36, 37, 30. I will not have 36 and a half, 37 and a half. I will have more levels in the area or in the region where it's more probable to have the signal. And this translates to terms of random signals, the regions where the signal is more probable, as we'll see. So let's start with uniform scalar quantization. How does it work? Very simple. My input signal, I will call it N, which is continuous in amplitude. And then this is my quantizer, G of. And then my output signal is V, which is discrete in amplitude. And the way we do this is to have something like this. The input-output relationship is like a staircase. This is my input. This is my output. And then I will have something like this. Whatever. So if your input signal, let's call this, I forgot what do we call it, A1 or X is later on. Oh, I don't have it here. Okay. whatever. Let's call this, I think A1. This is A2, A3 minus A1. We'll change it if later on it's the opposite, and so on. And this is X1, and this is X2 hat minus X1 hat minus X2 hat. So how does this quantization works? If my input signal is between, the value of the signal is between minus A and A, what's the output? 0. I will round it down to 0. It is between A1 and A2. I will consider it as X1 hat. If it's between A2 and A3, X2 hat. Greater than A3, whatever, X3 hat. Similarly, if it's minus A1 minus A2, it's minus X1 hat. Here, minus X2 hat. And then, regardless of how large my signal is, I will round it to minus X3 hat. So the signal that I'm quantizing will look something like this. I have some notes. It'll be something like this. Let's enlarge it a little bit. So I have certain levels that I will round my signal to, and as you can see, you will end up with errors that are rounded. Let's see how much is the error. But the issue is here, whatever you lose at the output of quantizer, there is no way to tell what was the original signal. Because after you cut it, there is no way to reconstruct the error resulting from quantization. Okay, so it's important to note that quantization error is irreversible. Yes. The error is the difference between the original signal and the quantized levels. You take the difference at any point. Here, this is not a very good figure because it's quantizing a continuous signal. Usually we sample and then we quantize. So it should be like for certain points only. So if we want to be in the context of what we are doing, I should not have, I should not have this. I should have something like this. I should have something like this. So this is my, what's wrong? No? Okay. Okay, so I should have something like this. I don't, you should have a sample signal, not a continuous signal. Sorry.
Doctor?
This is uniform. We are talking about uniform. Uniform means the distance, as you can see, those steps. Those distance. I don't know what's wrong with this. 1 second, the online question. 1 second. So as you can see, I don't know. Okay. No. The x-axis. Don't care. The output is the y, not the x. I don't know what's happening. Yeah, and the drawing is something wrong with it. Yes, question online. Hello?
So I was going to ask that we cannot recover the signal even.
Can you raise your voice?
I was going to ask we cannot recover the signal even if we apply infinite sinks.
Yeah, this is different. Quantization is different than sampling. يعني خلاص now we sample with more than Nyquist rate. If we don't sample the signal, if we don't quantize the signal, we can fully reconstruct it. But if we quantize it, there will always be what we call quantization noise. And next step is to model this error and see what's the relation between what's the number of levels and what's the signal to noise or signal to quantization noise value. Okay?
Okay,
but this is regardless of how fast you sample and how fast you reconstruct your signal. What you lose through quantization, you cannot reconstruct it.
Okay, thank you. Got it.
What do you mean? Anything between minus A1 and A1 will be rounded to 0. يعني probability of having something at A1 and at minus A1 is 0, right? But you have, once you want to solve problems related to this or design, you have to be consistent, either to include A1 to the left or to the right for all of them. You include them in the left or to the right in all of them, and it will be the same. طيب. So let's do some error analysis of and see the effect of quantization error. So let's do error analysis. So what do you want to do? Again, this is we'll do some assumptions first. So my input signal, and you have to tell me why I'm using n of t. Why I say n of t, not m of t. Hmm? No, it's not. This is the input, the quantizer. Okay, so this is sampled signal. What's wrong? Okay, this is a sample signal. I need a new, apparently, in this. I traveled over the weekend. I cracked the screen. Maybe this is why it's behaving weird. Anyhow, so this is my sample signal. This is a quantized signal. So assume, let's do some assumptions. Assume we use L levels. I have L levels of quantization. So in this question, how many levels do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 in this case. How many levels you have? So assume I have L. And we should mention that usually we use L to be 2 to the R. Why? Where R is the number of bits. Why is that? And usually what we do is like this. Assume that this is my input-output relationship. And I have this quantizer, whatever. Assume that I have this quantizer. So this, how many levels I have? 1. No, I don't want. This is 5. I want 4. 1 second. Okay, let's do this. So now let's say this is whatever, this is 1, this is -1, this is -2, this is 2. Very simple quantizer. And let's assume again that this is 1, this is -1. So now, if my input signal is, let's assume my input signal has, you sampled your signal. So first sample, it's 0.9, and then 1.3, then -2.5, -0.7, and so on. This is your sample. After you sample, this is what you got. You got 0.9, 1.3, -2.5, -0.7. What's the output in this case, according to this quantizer? One second. Says that شباب انتوا اللي online, nobody is alerting me that is.
Just now.
Oh, just now. Okay. Yes. Question who? I'm giving you the input output relationship. You should know. So if the input is 0.9, 0.9 is here, right? What's the output? Right? The output is, so the output is 1. And then for 1.3, 2. -2.5, -2, and then -1. Yeah, again, you have to have consistent criteria. So you put the one either to the right or to the left for all of them. Okay. So now quantization is usually done including encoding. So you give a binary code for each level. So if I have 4 levels, how many bits I do need? I need 2 bits, right? So for example, I have 0, 0, 0, 1, 1, 1, 1, 0. And we'll talk about next lecture why I put 1, 1 before 1, 1, 0. So now, after encoding, what's the output? For the 1, 0, 1, then for the 2, 0, 0, for -2, 1, 0, -1, 1, 1, and so on. You keep doing this. This is what you, at the far end, after the encoding, you will get a series of 1s and 0s based on the levels that you, how many levels that you have. And when we are putting it, we take each 2 bits at 1 level. Yeah, you will do a lot of stages before. Yes, yeah, but you have to keep in mind. Yani, every step you do at the transmitter, you have to reverse the receiver. But as we will see in the next chapter, and you might send this 0 alone if you want to use. You can put each bit on a symbol when you transmit it, or you can group 2 bits or 4 bits in one symbol, or 8 bits in one symbol. We'll talk about different modulation techniques, digital modulation techniques, after you take those numbers. Fine. So this is what you will do. So in this case, L equals 4. I have 4 levels, right? 4 levels. Level, 3, 4. So L equals 2 to the 2. So I need 2 bits, right? To represent the levels. Fine. So let's go back here. So I have again L equals 2 to the R. Assume that all levels have, or the distance between, assume that the distance between levels is delta. So this is delta. This is, assume, I know it's not drawn to scale. and define Q to be M minus V, where Q is the error, right? Quantization error. It's the difference between the input signal and the quantized level, right? Because if in this case, for the first sample, what's the quantization error? It's M minus V. M is what? 0.9. V is 1. So error at the minus 0.1. How about here? 2 minus 1.3, which is, sorry, 1.3. Now we define it what? M minus V. M is 1.3. V is 2. So minus 0.7. Third one, minus 2.5 minus 2. So minus 0.5. Third one, minus 0.7 minus 1.3. This is, again, this is not a good example, and delta is different.
This is an example of the non-uniform.
Yeah, this is not non-uniform, and this is not. Let's forget about this and talk about delta in general. It's the same. And you can have error. It depends on where your sample will be, right? If your sample, all the numbers between 0 and 1 will be rounded up to 1. So if you are less than 0.5, yeah, this is not a good example. Again, this is not a uniform. In general, let me do a simpler one. Let's do. Okay, like this. Okay. So this is correct now. So this is delta. All of them, they have the same width. This is delta. This is delta. And this is delta. And usually, when you design your quantizer, you will have this. This is delta over 2. This is, you choose it to be symmetrical. So what's the maximum error you can have? What's the maximum error you can have? Maximum error will be if your signal is just positive and then you round it up to the level, right? Because it's very close to this point, the error will be small. بس إذا كانت 0.01, you round it up to delta over 2. Or if you are here, if it's just minus 1, you round it to minus delta over 2. So the maximum error is, your error is Q, we know. Q is between delta over 2 and minus delta over 2. This is the maximum error that you might have on both sides, either delta over 2 or minus delta over 2. In your opinion, given that we do not have any other information about the signal, the input signal, what will be a reasonable distribution for the error? Normal? Why? Yeah, but in this case, we'll talk, the next one, we'll do error analysis for a normal input signal. But if I'm not telling you anything about the input signal, you have no reason to assume that you have more probability of the signal here or here or here. It's for you, it's all the same. So a reasonable and simple way, and it's used actually in many places, is to assume a uniform error distribution. 1 second. So a reasonable error distribution is the uniform distribution. So FQ of Q is uniform. I will come to your question. 1 second. Let me بس plot it right to Q, F of Q. So we said it's between 1 over delta over 2 and so uniform looks like this, right? What's this level? What's the height?
Area should be 1.
Area should be 1, right? So this is delta. And this should be 1 over delta. So FQ equals 1 over delta when Q is between delta over 2 minus delta over 2 and 0 otherwise. Question? What's the maximum يعني انت level that you quantize your signal to the width تبعه is delta. Okay? And it looks like this. So now if in this region all the points in this region will be rounded up to delta over 2. What's the maximum, what's the minimum value here? 0 تقريبا يعني 0.0001. If your signal has this value, what's the error? You round it up to delta over 2. And we said we defined the error is to be m minus b. So this is the maximum error will happen at this point. نفس الشيء لو كنت هون you are here شلون جهة ثانية؟ Yeah, usually you'll have this is delta over 2. If this is uniform, this is 3 delta over 2 and whatever 3 delta over 2 is the same. No. So this is this point. You round it up to what? 3 delta over 2. So this is 3 delta over 2. No, this is the width is delta. So this is delta over 2 plus delta is 3 delta over 2. So the error here is 3 delta over 2. This is 0 here between 0 and delta. So in that case, this should not be 3 delta over 2. This should be delta. If this was delta, delta over 2 delta. Yes. So if this was, and again, I did not optimize. We have tables for that because you have to do an optimization to write down what are the specific points. Let's assume that this is delta over 2, this is delta. So in that case, if in between the error can be 0 all the way to 3 delta over 2 minus delta is delta over 2. Yes. Again, usually we will not. There's a way to calculate what will be the points, but people have done this and put it in tables. What levels that you will use, the x-axis and the y-axis, and I have the table. I will show it to you. But generally, following this figure, because this analysis is based on this figure, for any value of the signal, this is delta, right? So either any value in here, you round it either up or down. So the maximum error you will have is either delta over 2 or minus delta over 2. Okay? So if we assume that this is a uniform distribution between delta over 2 and minus delta over 2, what's the mean for this? You remember? It's easy, should be easy. 0, right? The mean is 0. But what's more important in random signals is the variance of the signal. What's the variance? Variance of the signal, you can calculate it, of course, if you want. If you remember, variance is q square fq dq minus mu square q. If you do it for the uniform distribution, this should give you delta square over 12. Why the variance is important? Because when we analyze random signals, how can we calculate the power of a random signal? Power of a random signal is simply the variance of that signal. Now, deterministic signals, if I give you any signal, sine wave, and I ask you to calculate the power, how do you calculate the power of a sine wave? Take one period, you divide by the period, you square it, you integrate it, and then you divide by the period. This is the power. But if I give you a random signal, I tell you I have a random signal. What's the power of that signal? For random signals, power is the variance of the signal. So in statistical analysis, the power of the signal is reflected in its variance. So now this is an error signal. The power of the error signal is delta square over 12. So if delta is large, the signal has more power or less power? Less power? It's d square over 12. So if d is large, more power, which means more quantization error. The distance between the levels, you are not using many levels, only few levels, which means the distance between them is large. Then the noise error is large. If you are using many levels, then the distance between them is small. Then the quantization error is small. So the quantization error increases as delta increases, which means you are using less number of levels. So let's continue with our analysis. Assume also, yes, if you solve this, you'll get 12. Try to solve this. Q square is يعني روح هاي بتصير دلتا over 2 لدلتا over 2 Q squared 1 over delta dq والميو 0. Solve this, it will give you delta square over 12. Okay. Because any random distribution, any probability density function, it should have an area of 1 under the curve. So we know the width, which is delta, so the height should be 1 over delta. So that the area is, this is the maximum error. So if this is the maximum error, this is the maximum error بالنيجاتيف, max negative error. This area should be 1. Area should be 1. So we have the width, which is delta, then the height is 1 over delta, because 1 over delta times delta will give you an area of 1. طيب, so assume that the signal is symmetric. Which means your delta is symmetric with max and min, m max and minus m max. So assume your signal goes up to m max and goes down to minus m max. And you are using L levels. Yes. So delta will be, so if your signal is whatever, So this is minus M max, and this is M max. So this is the whole range of the signal. And then you divide it by L to get the number of levels. Okay? So delta, the distance, depends how many levels you are using. It's 2M max, we call it usually with signals, we call it the dynamic range of the signal. So this is the dynamic range of the signal. Your signal fluctuates between two values, so this is the dynamic range. Old? No, not necessarily any signal, but fluctuates between two values. I don't care what's inside, it's a random signal. I know that I don't need signal to be symmetrical to be able to quantize it. No. Yeah, you can quantize. I plotted this way, but I could have plotted whatever, any. Symmetric in terms of, in terms of amplitude, maximum and minimum amplitude. Okay, so symmetric with a max and min, that's what I mean by symmetric. With max and min to be M max and minus M max. So this is delta, which means the quantization error is what? The delta square over 12, which is what? 2M max over 2 to the R, right? L is 2 to the R square 1 over 12. So this is my quantization power, error power. Hi. Assume also the signal power is P. The input signal that I have, it has a certain variance, which is P. Then we will define the signal to noise ratio, signal to quantization noise ratio. And this is very common terminology in communication and in some other fields. Signal to noise ratio. You want your signal to noise ratio always to be high as possible. So what's the signal to noise ratio? It's P over, because this is the signal power, and this is the noise power. طيب. So what's this? This divide. So this is P over whatever 1 over 12 2M max على 2 to the R تربيع. So let's group them. So I have 12P over M max. Let me see how I group them. M square, and I have 2 square 4. M max 4 square, and then multiplied by 2 to the power R square تصير 2 to the 2R تطلع لفوق بتصير بال. Do you agree? Any question on this? طيب. So let's usually the SNR we express it in dB. We usually, and I have one pre-prepared slide on dB. I will just refresh your memory. Usually use dP for expressing the SNR and power in general. Communication, we use dBs. We don't use the absolute value. Let me review dB quickly. and then I will leave the الهيئة to the end, the absence. I think this is what you need to know about DB. If you don't know it, this is should be a good review. If you hear 10 dB or 12 dB alone, not dBm, not dBw, if you hear the word dB, 99.9% of the time we are describing a ratio between two things. Okay? If you just hear the word dB. If you hear dBm, which is more common than dBw, then we are talking about the power of a single signal. So if you hear dB only, it's usually the ratio between two signals, the powers between two signals. And like the signal to noise ratio dB is 10 log the signal power over the noise power. Okay? For the signal only, we use, again, for the dB, if the ratio is greater than 1, if the ratio is 1, if the signal power equals to the noise power, which means this is 1, 10 log 1 is 0. So 0 dB means the signal and the noise, if I tell you my signal to noise ratio is 0 dB, means the signal power equals the noise power, not cancel, it equals. If greater than 1, you have positive. If less than 1, if your signal power is less than your noise power, signal to noise ratio will be negative, right? If you recall, this is the log, crosses at 1. So below 1 is negative. For the signal itself, if I want to talk about my signal, my useful signal, or the noise itself, we use dBm. dBm is what? It's the power of the signal with the reference of 1 milliwatt. So if your signal is 1 milliwatt, then it's 0 dBm. If your signal is 10 milliwatt, then 10 divided by 1 is 10. Log 10 is 1, then it's 10 dBm. And you can have, I think, let me with the table, you can have the values, and you can find those tables all over. And I forgot where did I got them صراحة, يعني حتى أنا. I have them in a previous set of slides. So you can have this is the, if your signal is in milliwatt, then it's dBm ratio. As you can see, with 1 milliwatt, it's 0 dBm. And usually, you hear later on, if you work in circuits and in communication circuits mainly, all the signals you need, what's the sensitivity of your receiver, and typical values of the sensitivity of receivers, minus 70 dBm, minus 80 dBm. If you have minus 100 dBm, that's really good. Minus 100 dBm means that the signal is in the nanowatt. You can detect very low signals. Noise level, if you put your receiver with an antenna in a location that there's no transmitters, go deep, whatever. This, you can assume there's nothing. 1 second. If there's nothing, you pick only the noise, then you will see the level around minus 120 dBm. This is what we call the noise level. So anything below that you cannot see in most of the instruments. Yes. Question.
You have unshared the screen.
غريب. Okay, so this is the dBm. Let's go back quickly to what we were talking about. So signal to noise ratio, we said it was 3b over m square 2 to the 2r. So this is in absolute sense. If you calculate it this way, it will give you 10 or 100. Why, by the way, why do we use dBm? Why do you use that? Why do we use dBs? You might ask, why do you use dB? Because dB can compress a large scale into a smaller scale. يعني log the higher the signals is, يعني going من 1 to 100 is the same as going from 100 to 1000. Okay, 10 log 10 is 10. 10 log 100 is 20. 10 log 1000 is 30. So you increase your signal substantially, but in dBs, it does not go that large. And this is usually when you want to show your performance, you have to do it over a large range of signals. That's why people use dB in representing their results. So SNR in dB, it will be what? It will be simply 10 log 10 log 10 of this, all of this. And we know that if I have log AB, it's log A plus log B. If you have the log of two things, then this is 10 log 3B m squared plus 10 log 2 to the 2r. And also we know that I can take the exponent outside. So this is 10r log 4. And if you go to your calculator and do log 4, this is roughly 0.6. If you calculate log r is 0.6. So basically, you will see where I'm heading. Plus 60r. Plus 6r, sorry. So assume we have the signal power does not change. So P does not change. The M maximum minimum do not change. I'm changing only R. R is what? Number of bits, which is related to how many levels. So the higher the number of bits, because L is 2 to the R. So the more bits, if I'm using 2 bits, means I'm using 4 levels. If I'm using 3 bits, 2 to the 3, I'm using 8 levels. So every time R is increased by 1, SNR increased by how many dBs? Every time you increase R by 1, SNR increases by 6 dB. And 6 dB is a lot. And every time you add 3 dB, it's like you are doubling the value. When you in dB, when you add 3 dB, you are doubling the ratio in absolute sense. So 6 dB, you are doubling it twice. So even 1 bit, every time you add 1 bit, you are increasing your signal to noise ratio. And of course, your signal to noise ratio, you want it to be as high as possible. In the limit, if you use infinite number of bits, what should happen? It's going to be why? Because quantization noise will be what? 0. And if you divide it by 0, it's infinite. And log infinite is infinite, right? Okay. I will leave again. I have 7 minutes. So let me. Question? Okay. So this is, we did many assumptions to reach this equation for the signal to noise ratio. Let's a more general way to do this is to calculate the mean squared distortion. And here, as we will see, there are tables that will define what's your quantizer and how to do quantization. And this, what will, again, this is not in your in Lathis book. I think you can find this in Proakis and Salih book, one of the references that I use. But I find this analysis nice. That's why I decided to go over it. So a more general way to characterize the quantization error is to use mean square distortion. And this should work with any input signal. How do we define it? We define D is the expected value of M minus V squared, where M is your input signal, while V is levels that you are using, the exact levels for quantization. So if you tell me that my input signal is Gaussian, has certain mean and certain variance, then I can calculate. If I use a quantizer, that's the numbers are whatever. I will any shape. No, not this one, not like this. So if I have something like this, give me those. I can calculate what is the best point to quantize the signal by taking the derivative and calculating this, because you know how to calculate this, right? Expected value of M minus V square is simply, in general, M minus V square F of M dm. And then you can you take the derivative. I will not go and make it 0, and then you solve for these. So what's good is that if the input signal is Gaussian, then the best level points are tabulated in the following table, and we'll في ايش؟ Attendance, yes, I will leave the last 2 minutes. I still have 1 minute. So I will talk about this table, and in the recorded lecture, I will solve a problem in using this table. But this table, this is the optimal quantizer for if you assume your input signal follows the Gaussian distribution. And it gives you, based on how many levels you want to use, what will be the optimum spacing between the levels, and what's the corresponding distortion. Based on this, you can plot your quantizer and apply to the signal. I will solve an example. So if you have only one level means what? Yeah, so you will round all signals to what? 0. So you have one level. And if you round all signals to 0, on average, what's your distortion? Why? Again, this is the input is the input is normal of 0 and 1. It's a normal distribution that has 0 mean and a variance of 1.
Or -1.
So you are rounding all points to 0. So on average, error, how much error you are encountering? The standard deviation, which is sigma, which is 1, right? For normal distribution, if normal distribution 0. So on average, if you put expected value of all points, the far points, and that's the variance. This is the expected. What's the variance? Expected value of x minus mu squared. So if mu is 0, variance is not. Variance is 1. Well, I'll solve this problem. I'll stop at this point. I will go over this table again. But this is the meaning of having Qasim. It's like you're not doing it, you're just assuming that all points are 0. What's the error that if you like in estimation, if you want, what's your best guess? Ahsan estimator. If you know that the signal that's coming is Gaussian, it has 0 mean, can be positive or negative. The best guess is to have 0. On average, this is the best guess that you always have. If you said that, no, I will use 1, then you'll have more error because all the negative values will be far from the 1. 0 is the closest point to all points of the normal distribution. Anyhow, we'll talk about this next time, but let me take the absence, and then if you tell me your name, you can leave silently, please. Okay, sorry. Still. Okay. Hmm?